This is Project 1 Video 1, the pencil and paper part. I've got a Cartesian coordinate system. X, Y. There's a particle at the origin that's got some charge, and an empty point in space, point P, at coordinates, I'll call them X, Y. And we're supposed to find the electric field at that point in space. I'm going to indicate the position vector of point P relative to the origin, and I'll call that R, and R is equal to X times I plus Y times J, because the charged particle that's causing the electric field at point P is at the origin. The components of the vector R of point P relative to the charged particle are just the same as the coordinates of point P. X and Y are both the components of the position vector, and they're the coordinates. So got to find the electric field right there. I'm going to define a unit vector R hat, and the magnitude, well, let's calculate something I'm going to call E, and I'm going to use the actual charge rather than the magnitude of the charge. So if it's a negatively charged particle, I'm going to get a negative value for this thing I'm calling E. K Q over R squared. Now, the absolute value of this is going to be the magnitude of the electric field. And here's the thing: if I multiply this E times R hat, I'm going to get E, the vector E. Check it out. R hat is in the direction of Q toward P. If Q is positive, E comes out to be positive, and the vector E is so E would just be the magnitude of the electric field, and it's the magnitude times the direction. So it would work out if it's positive. On the other hand, if Q is negative, this scalar E turns out to be negative, and I'm multiplying that times the vector R hat, which is in the direction away from Q. A negative R hat will actually be a vector toward Q, so I'll get a vector that's got the correct magnitude and it's got the correct direction. So I'm going to think of this whole problem in terms of the IJK notation. So let's see. In order to calculate this E, I need to find out what R is, and R, the magnitude of R vector, R is equal to the square root of X squared plus Y squared. It's just the magnitude of the position vector. And then R hat is equal to the vector R divided by, say, times 1 over R, times 1 over the magnitude. Alright, this E is not really the magnitude of the vector, it's the component of the vector in the R hat direction. That is to say, any vector can be expressed as some value times a unit vector. The value is the component, the scalar component of the vector in the direction of the unit vector. And so it can be positive or negative. I'm analogously using a symbol that's just R with no arrow over it, no hat, to mean the magnitude of the position vector. Alright, I think I might already have down everything I need. So let's try to write out the code. So code 1, take arguments Q, and I'm going to call it rvec, which is really just it's got the x and the y, with that the I and the j are implied, so it's just going to be an x comma y. That's the second argument. Then calculate mag, which is going to be equal to the magnitude of rvec. So I can think of that as rvec of 1 squared plus rvec of 2 squared square root. Might be able to calculate it another way. I'm going to try that once we actually do it, but this works. Calculate r hat. I'll use r hat as the name of the unit vector, which is equal to rvec divided by r mag. So this is going to be, this is a 1 by 2. First element contains x, the second y, and I'm thinking of it as x times I plus y times j, but it's just a 2-element array. And when I divide that vector by this scalar, I get the x component of the unit vector is the first element and the y component is the second element. So this certainly isn't the only way of doing it. You know, you have to think about it in terms of IJK notation if you don't want to, but this is the way I choose to go about it. And then I think I'll go, I'm going to try evec. We'll calculate evec equals k times I guess I need a step 0 in this code. I'm gonna need k, so maybe I'll change these numbers. So 1 init initialize k equals 8.99 times 10 to the 9th, and then 2, 3, 4, 5. I guess 1 and 2, the order isn't really relevant, but and then evec is equal to k times q. I don't really need to use the asterisk here, but I will. The computer program itself, but k q over r squared, r mag, squared times, I will put the asterisk there, r hat. I got an r hat, and that's what I'm returning. So evec is going to be my return variable name as well. Calculating return evec equals that. I think I've got that good. That's working well. Let's I didn't say you had to in there, but we want to make sure this code works. So as a separate thing, that completes the code outline. So code outline, I'll put a title there. Let's calculate a test case. Test case. I'll let Q is equal to 5 times 10 to the minus 8th coulombs is a reasonable amount of charge. K we know. Let's have X comma Y equals 5. I'll go 5 centimeters, so 0.05 meters, comma point. Well, let's go 1.0 meters. No, 0.10 meters, so 10 centimeters. 5 centimeters, comma 10 centimeters. Then, so that would mean, by the way, that R is equal to 0.05 meters I plus 0.1 meters J. We'll have a lot of stuff to check here. R itself, which is x squared plus y squared square root, would be 0.05 meters plus 0.1 meters squared, both of them squared, square root, which is equal to 0.111803. 0.111803 meters. And then that's not R hat, by the way, that's R vector. So let's fix that up. R hat is equal to R vector times 1 over R mag, which is 0.05 meters I plus 0.1 meters J times 1 over 0.111803 meters. And that gives us 0.447215 I plus 0.89443J. And then let's see what else we got. We're going to get E. I think I'll calculate E separately, even though in the code I'm probably going to go the scalar E. E is equal to K Q over R squared. I'll calculate that separately, even though I'm going to do vec E, I think, directly in the code. Just in case things aren't working out, I'll have one more thing to be able to check. So that's 8.99 times 10 to the 9th Newton meter squared per coulomb squared times the charge. I think I got that 5 times 10 to the minus 8th coulombs. Let's check to see what I really picked. 5 times 10 to the minus 8th coulombs. And then divided by R squared, which is 0.111803 meters squared. And I am going to get the meters cancel out. I'm going to have newtons per coulomb in the end, which is the correct units for E. So E For this case, scalar component of the electric field in the r hat direction is 35960. I guess I'll go 0.26. Well, I don't know, I only had 3, 6 there, 2, 4, 5, so let's call that 0.3 newtons per coulomb. And then E is equal to E r hat, which in this case would be 35960.3 newtons per coulomb times 0.447215 I plus 0.89443 J, and it gives us the vector E is equal to 16080 16082 newtons per coulomb I plus 164 newtons per coulomb times J. So unless I've made mistakes here, and I guess I can consider the checks to be checks on both things, so if it doesn't work out I can look for mistakes here as well as in the code. But if I've done this correctly, then the electric field for this particular case should turn out to be 16082 newtons per coulomb I plus 32,164 newtons per coulomb times J. So I'm going to use that for a test case. You're not really required to specify a test case, but we do need to make sure the program's working, so we kind of need one. So you should do one. And I think that covers it for the pencil on paper part of project number 1.